as you can see, we are in this chapter starting to talk about three-dimensional figures, and we will start simply by talking about the vocabulary of those three-dimensional figures, and then tomorrow we'll start finding the area of those figures, and when we return from break, we'll be talking about the volumes of these figures. The chapter we just finished is tremendously important in order for us to be able to find the area and volumes of these figures. Once again, let's put these phones away. We're starting a new chapter. Let's get focused. Okay, so there are polyhedrons, and then there are other stuff. So as you can see in our notes, polyhedrons have line segments, and they have surfaces that are polygons. So what would be an example of, let's start with non-example. What would be an example of something that is not a polyhedron? If its faces have to be polygons and its edges have to be line segments. What would be an example of something that is not a polyhedron, right? Give me something that is circular that's three-dimensional. A sphere, absolutely. A sphere is not a polyhedron. There we go. Matthew, you were about to give me a non-example. A cylinder. Something else you can think of? Something else? Yes, ma'am. A cone. Okay, so what would be common examples of things that are polyhedrons? A pyramid, absolutely. What else? Cube, or more generic, pyramid and prism. Okay, so in this course, the figures that we're going to be talking about finding the surface area and volume of are those shapes. Everything else kind of falls outside of our requirements. So, as I mentioned before, in a polyhedron, the surfaces are all polygons, and I think I kind of accidentally said it. The surfaces are called faces of the polyhedron. The intersection of those surfaces are called edges, and the points where three or more of them meet are vertices. Yes, good. Okay, so to bring this vocabulary into our classroom, looking at our classroom, that wall would be considered which of those three? Is it a face, an edge, or a vertex? That's a face. How about that line up there? What is that? That's an edge, and then that corner, that's a vertex. Okay? Nothing too complicated. But we do need to know that vocabulary because later on in our lesson we have a formula that uses the number of faces, the number of edges, and the number of vertices. So in problem 1, we are simply counting them and identifying them. So how many vertices does this polyhedron have? How many vertices? It's got 4. They are R, S, T, and U. That's it. They're the points. How many edges are there? There's 6. Good. Edges, remember, are just the line segments. Our edges are U, our T, our S, and then UT, ST, and US. Fantastic. Finally, how many faces do we see? There's 4 of them. They're all triangles. So triangle RTU, triangle RTS, triangle STU, and SUR. For the problems in your homework, you may have noticed that I'm only asking for diagrams for numbers 15 through 17 and 21 through 23. And you'll find in this chapter that requirement of drawing the diagrams starts to fall away a little bit. And I'll be honest, it's because I wouldn't want to draw a whole bunch of these three-dimensional figures, so I'm not going to require that you do so. I would, however, urge you at least describe the diagrams. Remember, the idea, my philosophy regarding your homework is that you should be able to study from it. And I still hold you can't study from a bunch of answers. If you're not drawing the diagrams, at least describe them so that that's still something that you can study from. Okay? As I mentioned earlier, we need to make sure that we are strong in the vocabulary of what are the faces, what are the edges, what are the vertices, and being able to look at a diagram and count them, because we have a formula that relates all of them. It's Euler's formula. I always mispronounce it. It looks like you want to pronounce it Euler's. It's actually Euler's. And when we're looking at the three-dimensional figure, the formula is F plus V equals E plus 2. However, if you were to take a solid, a polyhedron, and cut it open and lay it flat, in other words, if you were to draw the net for it, the formula changes just a little bit to F plus V equals E plus 1. Okay? So in problem 2, they're asking us to determine how many edges the polyhedron has. Now granted, you can look at the diagram and count them pretty easily enough. However, in the interest of using the formula before you do it on your own and not your turn, let's go ahead and use the formula to find the number of edges. Edges plus 2 will equal the number of faces plus the number of vertices. How many faces does the figure have? It has 8. There's 4 going around the top and 4 going around the bottom. And then how many vertices does it have? It has 6. The top point, bottom point, and the 4 points going around. So solving our equation, we've got 14 equals E plus 2, telling me that I have 12 edges total. Please take a moment, work through your turn within your group using Euler's formula to find the missing value. From what I'm seeing and hearing, we're ready to move on. There we go. Okay, the solutions to part A and B are on the screen. If there's any discrepancy or confusion, let's make sure that we talk about it before we move on. All right. So the question was asked of me, Mrs. Clouse, what do they mean by verify Euler's formula? What they're wanting us to do is count up everything plug it into the formula, and make sure that left side equals right side. Right? So in part A, let's first identify how many faces does this solid have? It has 6. How many edges does it have? How many edges? I think I heard it. It's 12. Be careful. Eyes up so that you're seeing the 12. There's 4 on the top, 4 on the bottom, and then 4 along the sides connecting top to bottom. And then finally, how many vertices does it have? It has 8. There's 4 points going around the top and 4 points going around the bottom. So all they're asking us to do in part A is take those numbers, plug them into Euler's formula, and show that left side equals right side. Okay? So I would have 6 plus 8 equals 12 plus 2, and that is a true statement. Easy enough. In part B, they're asking us to draw a net for the solid. Remember, we've done nets before. That's where you're cutting it open and laying it flat. So, yes. That's one of the problems that I'm asking the diagram for. There's only 3 of them. So, if I'm drawing this, some of you might say it would be easier to lay the 4 rectangles down flat and then have a trapezoid folding over on the bottom and another trapezoid laying over on top. Okay, so it's not going to be to scale, because goodness knows I can't draw. But we'll have the 4 rectangles folding over from the top, and then a trapezoid folding over on this side, and then another trapezoid folding over from here. Again, the diagram is not drawn to scale. There's no measurements in this diagram, so we don't have to worry about that. It's just asking us to lay it flat so that we can use part C. Yes, ma'am.
Can you draw the other trapezoid very nicely?
Yes, absolutely. Absolutely. All right, so finally in part C, they're asking us to verify the formula for this 2-dimensional net. So let's count everything up once again. How many faces does the net have? Still has 6. How many edges does it have? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Want to see that one more time? See? Okay. You heard me counting, but you weren't watching. All right. So, as I'm counting it, I think it's easier for me to keep track of things if I start here and go 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Vertices, you have 14. Makes sense? Yes, ma'am.
I thought that edges were only like where the 2 and 6. So
The edges are the line segments. And when we plug it back into Euler's formula, you'll see that our numbers do in fact add up often. How do we count the vertices? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? Remember what I said. in the end, you'll see that everything adds up. Once again, the formula is F plus V equals E plus 1. When you're looking at it two-dimensionally, notice what we have. We have 6 plus 14 equals 19 plus 1. So we did, in fact, count things correctly. They're on this screen. Okay. Second part of our lesson has to do with cross sections. And a cross section can be thought of as just a slice of a three-dimensional figure. Okay? So let's envision a couple of things. I have this three-dimensional figure. If I were to slice it, let's pretend that this is like perfect and cylindrical, or this is a very bad cylinder, but get the, kind of envision that it's perfect for me. I'm sorry? Somebody just gave it to me at the beginning of the year and said, maybe you can use it later on in the year. Right, I'm using it. Okay, so let's pretend that it's perfectly cylindrical. If I were to slice it down vertically and cut it open and show you that slice, two-dimensionally, describe what you would be looking at. Okay, if I cut this open with a plane, if I hold it open to you, and you're just thinking of it as a two-dimensional figure, what you'd be looking at would be a rectangle. That's a cross-section. Perhaps this cross-section is easier to look at. If I were to take this cylinder and cut it open horizontally, and then take that slice and show you, you'd be looking at a circle. Okay, that's what a cross-section is. All right? Let's get wild and crazy here. How about if I take this and slice it vertically? What cross-section would I have? Triangle. Whereas if I slice it perfectly horizontally, I'd be looking at a square. Okay? So on the screen, they have drawn a cross-section for us. The plane is slicing that cone vertically. What cross-section is formed? A triangle. How about kind of just trying to take this to the next level? Suppose I were to take that cone and slice it horizontally with a plane. What cross-section would I have? Circle. Still getting really wild and crazy here. How about if I sliced it kind of on a slant? What kind of this? If I were to slice this on a slant, what kind of cross-section would I have? It wouldn't be a circle, definitely not be a triangle. What I'd be looking at would be an oval. It is not a circle. Actually, the proper term that you're going to see next year in Algebra 2, the proper term is an ellipse. Okay, so just kind of throwing that out there, and you'll be writing the equation of that and graphing that next year. Okay, in problem 4, that's a your turn. Please take a moment within your group and identify those cross sections. Okay, before we move on to drawing the cross-section in problem 5, please check your answers on the screen. Yes, great. One of the ways, gentlemen, one of the things that the book says is if you're having difficulty identifying the cross section, then you're dividing it with a vertical plane. So the way that the book describes how to mentally picture that is visualize that figure with the plane going through it, and sometimes you need to kind of mentally turn the figure so that the plane of intersection is like parallel to your face, right? So if you're holding that, I think it's called a frustrum, in front of you, it's almost like this, not quite cylinder thing, this bottom part of it. If this kind of jutted out a little bit more, you'd be looking at what you have on your paper, okay? And if I were to slice this open vertically, then what you want to look at is this shape right here that's in front of you. And you're seeing it a little bit more clearly now? All right. So the last thing that we're looking at in today's lesson is drawing a cross section. And once again, I know it's kind of a pain. That's why there's only 3 of them in your homework. So in problem 5, we are asked to draw the cross section formed by a vertical plane intersecting the right and left faces of the cube. So this is the right face, and this is the left face. I want a plane that's intersecting those 2 faces of these 2 faces of my cube. And what am I guaranteed that it will be? A rectangle. It could be a square, but it would be a square if I was slicing it perfectly halfway. Whereas, kind of, if my plane is slicing here and here, you see that it would not be a perfect square. The cross section would be a rectangle. Rectangle, yes. Yes, ma'am.
Could you do it so that like the plane faces it like that way? Like
Oh, so it's kind of at a diagonal?
yeah.
Yes, that is also. Actually, no, I'm sorry. It does say vertical. Vertical, in this context, we do want vertical meaning straight up and down. Okay, thank you for bringing that up. Question, sorry. Okay, give me one moment. I will be activating the daily quiz, and the questions for it are on the screen. Just give me a moment. It's not activated yet.